Hello. Yes, we are back again. What we are discussing? We are discussing. Sorry. We are discussing. Okay. Say for example, this is the pulse that having same frequency that was launched, but due to this nonlinear refractive index, the pulse will be changing its phase and keep on changing, and that will be as phase will be changing, their frequency will be changed, so that will be producing different frequencies in it into it the so that will be giving us more number of frequencies, uh, and so that will be changing the modulation, giving us a modulation in the phase, that is appearing due to the modulation in the phase, due to the self phase modulation appeared uh, in the pulse. There will be a generation of several new optical pulses of different frequencies, and that will be giving us a bandwidth of different uh, bandwidth of this in the spectrum. So that is the case of self phase modulation. Okay. So next topic is cross phase modulation. In the self phase modulation, there is only one pulse that will be propagating. Uh, let's say E is the electric field that propagated. Then what it will do? It will produce a phi. Phi means phase modulation phase, and that phase will be having an equation n plus n2 I into k naught l, where l is the fiber length, k naught is the wave number, and lambda is the wavelength. So this formula shows that SPM causes a nonlinear phase shift that is intensity dependent, because phi SPM is equals to n2 into E mod square. E is the electric field intensity. If it is having a squared mod square, then that will be intensity. So it will be intensity dependent phase shift. So if the intensity will be increased, then more phase shifting will be occurring, and because of more phase shifting, there will be large production of frequencies, different frequencies. If that will be happening, then our pulse will be broadened enough. Okay, the effect of SPM can be observed through a spectral broadening of ultra spectral. See, the term spectral broadening is appearing here. Spectral broadening of ultra short pulses, or the formation of optical solitons. Okay, two kind of thing can be happening. One is spectral broadening, and also the formation of optical solitons. Okay, now next topic is cross phase modulation. Here you can see a cross phase modulation will be there. For for the occurrence of cross phase modulation, you require a two wave two optical waves. Okay, means two electric fields should be applied, and they should be applied to a nonlinear fiber optics, a nonlinear fiber. And if that is uh, if the fiber will be having high nonlinearity, then what will happen? The uh, phase of one pulse will be changed by the other. Okay, so these two waves that you have applied to an optical fiber, then what these two will be doing, these two will be changing each other's phase. If that is happening, then what will happen? There will be a change of uh, there will be a change of phase in both the pulses, and that will be giving us a large number of new frequencies, and if the number of frequencies are going on increasing, then the pulse will be broadened enough. So that is another part. Here what it says, in order to observe XPM, two electromagnetic fields with different wavelengths, direction of state of polarization are required. In this case, one of these fields experiences nonlinear phase shift in the presence of the other. See what we have discussed. Assume that two optical fields having angular frequencies omega 1 and omega 2 travel through an optical fiber in x direction. Then the electric field will be composed of this summation of these two electric fields, and the nonlinear phase shift will be having nonlinear phase shift originating from XPM on the electromagnetic field omega 1 will be, see, the omega 1, the field E1 is giving us omega 1. So omega 1 field, there in the omega 1 field there will be a change of phase phi xpm, which is introduced by E2. E2 means the other field. Omega 1 is the field 1. Field 1 is in the field 1, the phase is modulated because of field 2. Okay, so similarly, in the other part also, in the omega 2 also, we'll be having an phi xpm, which will be changed by induced by E1. So these two optical fields will be changing each other's phase, and that will be producing the new frequencies, and because of new frequencies the pulse will be broadened enough. So these are the two uh, phenomena that are appearing because of nonlinear refraction. Okay, then the figure of merit is not required. Then pulse propagation in optical fiber. Here, uh, when an optical pulse, an intense optical pulse, of ultrafast optical pulse propagates through nonlinear media. Say for example, I am coming here again. Okay. Hmm. Yeah. Okay. Let us consider there is a fiber. This is an optical fiber, and if a pulse is launched here, okay, this is a pulse. Say for example, that pulse will be facing this all the characteristics of this nonlinear fiber. Say for example, this nonlinear fiber is dispersive, and there is a high nonlinearity. Okay, dispersive and nonlinear. So what it will be having? It will be having four things. One is yes, the characteristics of this pulse when it will be propagating through this nonlinear fiber. Then it can be studied by an equation which is called nonlinear Schrodinger equation. Okay, and in the nonlinear Schrodinger equation, what are the parts? This first part is called the dispersion. The second part, second part is the pulse form. This is the pulse form. I'm calling as PS, pulse form. This is the loss parameter L, and this is the nonlinearity. Okay, so there are four parts are there in the nonlinear Schrodinger equation that describe the propagation of the optical pulse into the fiber, and this nonlinear Schrodinger equation contains one is dispersion. Dispersion means what dispersion gives is dispersion gives how the propagating pulse will be dispersed when it will be propagating through this nonlinear dispersive medium. So beta 2, here you can see beta 2, the group velocity dispersion is there. So group velocity dispersion determines the characteristics of this dispersion. Now this is the pulse form. In the second part is the pulse form. Pulse form means, say for example, this is the beam of this laser, which is going to propagate. Okay, so uh, so there will be a special distribution of this pulse. This is the special distribution, which said it will be it will be looking like this, and that actually this is wrong. The pulse should be like this. Okay, this is Z. Okay, so and this is the intensity, or we call here A. Okay, so this is the pulse form, and the pulse form, let us consider this is a in the form of a beam it is propagating, and this form will be given by this part, the second part, pulse form. How it is behaving, before its entry to the optical fiber will be given by this second part. The third part is the loss. Loss means when there will be some the loss parameter may be occurred here. Loss parameter may be having a relation with distance. If we know that when a light propagates through an optical media, that there will be a loss due to lot of phenomena, lot of effect. The loss will be there, and that loss is counted as this part. Here alpha is called the loss parameter, and the fourth part is the non-linearity. This gamma basically is called as the non-linear parameter, and this determines how the non-linear effects will be giving us the all the non-linear phenomena. Okay, non-linear phenomena like self-phase modulation, cross-phase modulation, soliton generation, etc., etc., four-wave mixing, etc., that will be counted by this part, the fourth part, non-linear part. Now let's move with this. Okay, now you see here beta 2 is the group velocity dispersion parameter. A denotes the slowly varying envelope of the pulse. Alpha is the loss parameter, and gamma is the nonlinear parameter. Gamma is given by an equation, omega n2 A effective into C. So A effective is the effective area of the fiber core. So if we solve this equation, then we can get the value of, this is a differential equation. Okay, if we solve this equation, then we get the equation, the expression of A, the slowly varying envelope, and that A will be becoming this one. Okay, that is the expression of A is kind of this. So this way, what we can count how the pulse will be propagating through optical fiber, and all other phenomena of soliton propagation, self-phase modulation, cross-phase modulation, four-wave mixing, and all the phenomena related to the dispersion can be studied by this equation, which is called nonlinear Schrodinger equation, which deals with the pulse propagation in optical fibers. Okay, with this we stop here, and we are next two topics are remaining that will be discussed in the next part.